In this video, we'll work an application example problem for antiderivatives. So this is a problem I wrote probably beginning of 2012, maybe end of 2011, so quite a while ago. Basically what I did was I went to the Census Bureau's website, the U.S. Census Bureau, and I looked at their data for the year-to-year population changes. And I can't remember if I looked only for the actual census year data, just every 10 years, or if I also used their year-to-year projections, for every single year. But as I recall, I used the data for the past 150 years, basically every census that's ever been done. And I took that data, and I think I put it in Excel probably, and I got a best fit exponential curve for that data. So that's this function right here. I know this is not the best quality. I was basically trying to get this thing onto into Notability, and taking a photograph of my computer screen was the best I could do. So there we go. Anyway, so the best fit curve was P of t equals 2.3508 times e to the 0.00763 t power, and this P of t is in terms of millions of people. That's just to keep the coefficient smaller, and t is in terms of years. So that model is based on the data that I had at the time, so it's kind of old, but it doesn't have newer data. Also, the estimated population for January 1st, 2011, which is another feature they have on the website, you could pick any day, as I recall, and get that estimated for that day. So this was 310,543,897 people in U.S. population at that time. Now, sorry, I'm struggling with the iPad a little bit here. This 7 at the end is probably not accurate. How can they possibly know to the day how many, or down to the individual person how many people there are? And in fact, that day, as they were typing this up, someone died or someone was born. So this 7 is just not reliable. It could have been a 0, but however they did it, they had this approximation. The 9, not very reliable. The 8, not very reliable. The 3, not too reliable. The 4, now we're starting to get to where, yeah, this is probably reliable. Well, I'm not a statistician, so maybe, in fact, it's only the last 2. Sorry, struggling with the iPad again. Maybe it's only the last 2, the 9 and the 7, that are not accurate. But certainly, the 310 is totally accurate. They know down to 1 million people how many of those there are. So, and that's, again, this is January 1st, 2011, and also, as I've mentioned, the t is in years. Sorry, struggling with the iPad again. And then also, yeah, it's a little bit laggy. Maybe that's okay. And then t equals 1 corresponds to 2011. You might be expecting t equals 1 corresponds to the year 2001, or the year 1 even. But no, 2011, just to keep things somewhat simple, because we don't want huge numbers. So how do we do this? Well, basically, this is called an initial value problem, because we are given a rate of change. How is the population changing over time? And we were given an initial value. At some point in time, it was this amount, okay? So what I want to do is I want to find the antiderivative of this function so that I can find not a rate of change function for the population, but just a population function. So P of t, or I should say capital P of t, will be the antiderivative of little p of t dt. So this is the antiderivative of 2.3508 e to the 0.00763 t power dt. Okay, let me reach for a calculator, which I'm going to need in a few minutes. Okay, so you might recall from a previous video that as a formula, the antiderivative of e to the k t power dt, we called it x previously, but we'll go with t for now because that's what we're using. This will be 1 over k e to the k t power plus c. Okay, so that's what we'll do here. This is equal to 2.3508 over 0.00763 to the 0.00763 t power plus c. I'm going to switch to a thinner stylus tip because that might be a little bit clearer to read. Anyway, this is basically our population function, but there's that pesky plus c. We don't know what c is yet. That's not equal to the initial value, but it's in some sense equivalent. We can use the initial value to find it. So going back up here, the change colors here. The 310,000 and 310 million and change, that is the population on January 1st, 2011. So if we use that initial value, and we'll say that t corresponds to 1, as we said earlier, or t equals 1 corresponds to 2011 rather. Well, then since I'm using the initial value at the beginning of the year, day 1, then when I use my function, that will mean that it's the current year, but the first day would be standard. So like 2018, for example, t would be 8, but that would give you the first day. So if you want like halfway through the year, you should use 8.5, okay? So when t is 1, then p of t, or I should say big P of t, will be 310.543.897, 310 point whatever, because this is in millions already, and I don't want to use 300 million if the scale is already in terms of millions. So that means that 310.543.897 is equals 2.3508 over 0.00763. Let's be a little bit neater about that. 763e to the 0.00763 times 1 power, because again, t is equal to 1 plus c. What I can do now is I can subtract this to go on the other side. So 310.543.897 minus 2.3508 over 0.00763 times e to the 0.00763 power. That equals c. All right, and a bunch of the microphone there. Hopefully, not a bunch of sound from that. So I need to throw this into a calculator and get a decimal number. Well, I've done this problem enough that I just remember that c is approximately 0.0. Is it 2 zeros? Well, 84499. Yeah, that's correct. 1 0. Okay, let me fix that 9. So that means that big P of t, this is 2.3508. And I'm going to leave this coefficient as a fraction with decimals, and I'm not going to worry about cleaning that up. It's not super important right now. 763 plus 0.08499. And you might think, well, why do we care about such a tiny number? We're adding 0.08. That's like 1/12. It's a tiny amount. Well, remember, this is in millions. So this represents a little over 84,000 people. So that's, that's a significant amount. That's not negligible, given that the scale of the function is in millions to begin with. So there we go. So if I wanted the population at the beginning of, say, the current year, so the current year is 2020, right? So that would be what t equals 10, right? So if I wanted January of this year, I would do p of 10. So this is 2.3508 over 0.00763 e to the 0.00763 times 10 power plus 0.0844499. And I can throw that into a calculator and get a decimal approximation to see how much that was. So, or is 2.3508 divided by 0.00763 times e. There it is. I don't use this calculator very often. To the 0.00763 times 10 power plus 0.0844499. Okay, so I get about 332.612,187. So that corresponds to 332,612,187 people at the beginning of the year, January 1st. Now, what if I wanted to know the exact well, it's an approximation. I'm using an estimate, of course, because I'm using a mathematical model based on old data only. It hasn't been updated with new information. So what if I wanted the population today? This is April 15th. So I'm going to cheat a little bit. I'm going to go to the internet rather than counting by hand, although we could. That wouldn't be super difficult, but I'm going to be lazy. Let's say, which day of the year is it? The current day number, that's what I want. It's day 106. Okay, so we are at 106 out of, is it a leap year? I can never remember. It is a leap year. Okay, so 366 days. So what is that approximately? 106 divided by 366. So we're about 29% of the way through the year, so 0.2896. I'll say 4 decimal places is plenty. So that means that now corresponds basically to t equals, approximately 10.2896. Okay, so I want big P of that. Big P of 10.2896. This is going to be 2.3508 over 0.00763 times e to the 0.00763 times 10.2896 power plus 0.084499. I have this mic in a really bad position. I keep bumping into it, so hopefully it's not making too much noise. So 2.3508 divided by 0.00763 times e to the 0.00763 times 10.2896 power plus, move out of the exponent there, plus 0.084499. Now I'm nervous that I did this wrong on the previous one. Oh, syntax error. Okay. Oh. Yeah, okay. I'm used to a different calculator, so I put parentheses where I didn't need them, so I'll delete that, and hopefully, yeah. Okay, so this is about 333.3, that's the last 3, 769. So that corresponds to about 333,347,769 people. And as before, that 9 really is not reliable at all. But, maybe the 333 is. So let's look it up. Let's go to, I guess, census.gov/popclock. That's the population clock. So census.gov/popclock. What do we get? So the current estimate from the Census Bureau, the one that that they have their models going, they have newer information and they're much more sophisticated models. Really, the population is about 329,523,454. So that's off by about 4 million people. So it's just over 1% off. So that's pretty good. Remember, this is using only old data from like 8 years ago, longer than that, 8.5 years ago. And I was able to rebuild a model using an antiderivative and the initial value and get a function that's actually pretty accurate. Even now, this would be a usable estimator, right? You're off by 1%. Big deal, right? That's pretty close. That's definitely usable. So that's just an example of an initial value problem, why you would care to do this. So we'll be doing more of these in later videos where we have different antiderivative techniques. So for this one, the antiderivative step really was not that difficult. It was just basically this formula. It wasn't super hard. We'll be doing more complicated ones later as well.